Okay, I will briefly introduce myself. My name is Germa Ferrari. I'm a master's student at the Basic Science program of the University of the Republic in Uruguay, and I am a teaching and research assistant at the Operational Research Department at the same university. The objective of this talk is to show you an embedded domain-specific language to work with Mathprog models inside Scala and the techniques I use to encode its syntax. What I hope you get out of this presentation is an idea of how Scala can be used to encode a moderately complex language using the implicit infrastructure and type classes. I will start by introducing Mathprog and the kind of problems that can be expressed by it. Then I will show some examples of the DSL and the Scala features used. And I will finish talking a bit about the implementation of the encoding of one of the operators. So, GNU Mathprog. Mathprog stands for mathematical programming, which, despite the name, has nothing to do with computer programming. So, mathematical programming is another name for mathematical optimization. So here, in this context, a program can refer to some plan or schedule that we want to optimize. So Mathprog is a modeling language for mathematical programming problems. For example, in a typical workflow, we can have something like this. We have some optimization problem, some problem for which we want to find the best solution to. Then we write a pure mathematical model. Then we write it in some language that can be understood by the computer, and here is where we can use Mathprog. And then we run computational experiments using different data instances. By computational experiments, I mean running some program that knows how to solve these kind of problems. And these programs are called solvers because of that. So, for example, the GNU Linear Programming Kit is a free software package that that includes one of such solvers and support that you use a Mathprog model to specify your problem. The kind of problems that can be expressed by Mathprog are all linear and can have either integer or real variables. And these problems are called mixed integer programming because they allow integer and real variables to mix. So this is how it looks, a generic mixed integer programming optimization problem written in Mathprog. Here, what we are saying is that we want to find x and y that minimize some function f while satisfying some constraints g. X and y are called the decision variables. They model the decisions that we want to optimize. The function f is called the objective function, and it's a measure that we will be using to say that one decision is better than the other. And the constraints g are equations or inequations that our decisions must satisfy. So in this case, we have an inequation. And both the objective function and the constraints must be linear. That is, they can only be composed by sums of multiplication of variables and constants. So this is the full model. Here we are adding the declaration of the parameters, the sets, and the variables. Here we have the declaration of the variables. X here is an integer variable and has a lower bound of 0. And y is a real variable because all the variables are real by default and also has a lower bound of 0. This is the declaration of the parameters. We have some simple parameters and other parameters that are indexed by some sets. And this is the declaration of the sets that we are using to index the other declaration. Here we are using the assignation attribute to specify directly in the model the value that we want to use. In this case, we are using what Mathprog calls an arithmetic set, which is a range of numbers. If we don't do that, we have to specify these values later along with the other parameters data. So, okay, we are going to embed Mathprog in Scala. So the first question that you probably have is why do we want to do that? So this is an incomplete list of things that I want to do with Scala. I want to programmatically generate the constraints. I want to be able to transform my models and create new ones, for example, by splitting some variables. And I want to develop alternative resolution algorithms using all the information that Mathprog has and working at the high level of abstraction. So in order to embed Mathprog in Scala, we basically need to do two things. We need to represent its syntax in Scala, and we need to define some semantics. So we can use the EDSL for something else than writing the model. For example, we can generate Mathprog and use that to call the solver. So we are going to do a deep embedding of the language. So for the representation of the model, we are going to use an encoding of the abstract syntax tree of Mathprog using case classes and seal traits. And to mimic the Mathprog syntax, we are going to use some methods as smart constructors for some parts of the AST and other functions that will allow us to combine some trees and create new ones. So this is the first example of the EDSL. Here we have the declaration part of the model we saw earlier. On the left, we have the Mathprog version, and on the right, we have the Scala EDSL version. We have three basic smart constructors for the sets, the parameters, and the variables. For sets and parameters, we are using the same word as Mathprog, but for variables, because var is a reserved word, we are using xvar. And these smart constructors return the abstract syntax tree that represents these parameters. For example, of these declarations. This is the AST of the C parameter here. We can see that it can get pretty big even for simple terms. So one thing that we can see here is how we define the arithmetic sets. We can use the same notation as Scala ranges. In this case, we are not creating a range because M, N, and L are not numbers, they are parameters. So this is creating an abstract syntax tree that represents this arithmetic set. Another thing that we can see here is that we can use Scala var args to represent the simple cases of indexing. And for more complex cases, we can use a specific syntax that the EDSL provides. Here we have the declaration of the variables. To say that one variable is an integer variable, we just call an integer method, and this will create a new variable with the integer attribute added. In the same way, to specify the lower bound of a variable, we just write greater than or equals some value, and this will create a new declaration of the variable with this lower bound attribute added. So every time we call these methods and operators, we are creating new values. We never modify anything, and this is on purpose, so everything in the EDSL can be immutable. Okay, this is the objective function and constraint part. We have two more smart constructors. For the objective function, we can use minimize. We can also use maximize. And for the constraint, we are using an abbreviation of subject2. We are using ST. So one thing that we can see here is that we are using multiple parameter lists to separate the name and the indexing from the expression in both the objective function and the constraints. This allows us to use var args for simple cases of indexing, and also helps it look more similar to Mathprog. We are also using multiple parameter lists in the summation for the separation of the indexing and expression being added. Here we have examples of addition, multiplication, and summation. And to reference the individual parameters, variables, or sets, we just apply them to some indexing value, and this is similar to how we do it in Scala with arrays or lists. And to define a constraint, we just use the less than or equals operator. We can also use the greater than or equals operator or triple equals. And if either the expression on the left or the expression on the right are linear expressions, then we will be creating a constraint. And Mathprog linear expressions are expressions that involve involve variables. Okay, and here the ST smart constructor is receiving a constraint and is creating a new one, adding the name and the indexing specified. So now I'm going to talk a bit about the implementation of the syntax. Most of the implementation of the syntax. So many of the syntactic constructs that we want to implement require a broad and possible open number of overloadings. We also want to be able to use them using an object-oriented style. We want to say some value dot method arguments or value operator arguments. So this will lead us to use type classes and object-oriented forwarders. And this, in turn, will lead us to use implicit prioritization. So I will try to show and motivate this by an example. So I will show the implementation of the greater than or equals operator. So here we are using greater than or equals to define the lower bound of a parameter. The param smart constructor returns some data type param stat that is part of the AST. Because we want to treat the AST as just data, we don't want to add any syntax-related method to it. So we are going to add this method using an implicit conversion. And we need to handle many overloadings. For example, we can use a Scala numeric type to specify the lower bound or another parameter, or we can use the greater than or equals operator with variables, or to compare two numerical expressions and create logical expressions or expression, or to compare two linear expressions and create a constraint. One thing that is important here is that the result type depends on the types of both arguments. So one thing that we can do here is to use an implicit class to add this operator that is generic on both the types of the left argument and the right argument and the result type. So this class is fully generic and has a type parameter A, which represents the left argument, and defines a method with two type parameters that represent the right argument and the result type. But because this class is fully generic, we can have here the different implementation of the operator because we need the concrete types to do that. So instead, what we do is to ask for some implicit instance of a trait that represents our operator. So here we have this trait GTE op, which has three type parameters and defines a method GTE which will have the implementation of the greater than or equals operator for this combination of types. So this trait here is working as a type class. Once we have this instance, we can forward the implementation of the greater than or equals symbolic operator to the GTE method in this instance. So now, with this machinery, we can have the greater than or equals operator on every combination of types for which we have an instance of this type class. So we are changing our problem to define the right instances and its priority. And one thing that is worth mentioning here is that we are asking for the implicit instance at the method level, so Scala can use both the types of the left and right arguments to do the implicit search of this instance. This is what allows to have implementations that depends on both types. So the problem is now to define the right instances. So I will show the most relevant ones. I will show only the type because the implementation is not really important here. So this is the instance that allows to use the greater than or equals operator to define the lower bound of a parameter. It is an implicit def, not an implicit val, because we want to have a type parameter, and it's creating an instance of our trait, that our type class, that has a parameter as a left argument, some generic A as in principle as a right argument, and will be returning a new parameter. And for this generic A, we are asking for the existence of an implicit function that can convert this A to a numerical expression. So this in Scala is called a view bound. And this is putting, in fact, a constraint on all the possible types that can be used here. So it's generic as long as you have this implicit conversion. So with this, we can use greater than or equals to define the lower bound using any numerical expression, but also any other type that can be seen as a numerical expression. So this is the instance for the variable. variables, it's pretty similar to the instance for parameter. In this case, we're asking for a variable as a left argument. This is the instance that allows to compare two numerical expressions and create a logical expression. In this case, we have two type parameters. We are creating an instance of the type class that is generic on the left argument and the right argument and create a logical expression. But again, we are using view bounds to constrain the possible types that can be used here. So with this, we can compare any two types and create a logical expression as long as there is an implicit conversion from such types to a numerical expression. This is the instance for the linear expression. It's pretty much the same as the numerical expressions. This is what allows to use the greater than or equals operator to create a constraint. In this case, we are asking that the view bounds be to linear expression, and we are creating the constraint. So with this, we are satisfying all the requirements that we have regarding the overloadings, the way we want to use the operators. But we have still one problem. The problem is that these instances are ambiguous as defined. So for example, the instance for the numerical expressions and the instance for the parameters are in conflict because the parameters can be implicitly converted to numerical expressions to allow to write things like param p2 greater than or equals p1. So the parameters can be used as the left argument or using any of the two instances. And the instance for the numerical expression is in conflict with the instance of the linear expressions because every numerical expression is a linear expression. So they trivially satisfy the view bound of the numerical expressions. So when we have this kind of problem in Scala, one thing that we can do is to try to use implicit prioritization. In Scala, the implicit that you define, the implicit instances that you define in a trait from which you are extending have a lower priority than the instances that you define in the trait itself. So if you write something like this, the instances for the parameters and the variables will have the same priority, but they will have a higher priority than the instance for the numerical expression, which will have a higher priority than the instance for the linear expressions. And with this, we can solve all our ambiguity problems. Okay, I'm about to end. These are things that I'm working on or I want to work on in the future. I want to add new semantics, for example, to talk directly to the solver's API, so I don't have to generate Mathprog to solve the problems. I want to add more static controls, so I can check, for example, at compile time that the arity of the expressions I'm using to index other declarations have the right size. And I'm working to support other problems beyond mixed integer programming. For example, I'm working in supporting multi-stage stochastic programming problems with discrete scenarios. These problems have a fairly standard encoding as mixed integer programming problems, but you need to add some constraints to keep consistency. And also specifying the data, it's painful because you need to specify your values for every combination of stages and scenarios. So all these problems can be alleviated using the embedding. We can generate the constraint, or we can provide a more specific API to specify these values for these stochastic parameters. On a final note, I just want to mention that all the code present here comes from a project in which I am experimenting with working with Mathprog in Scala at a high level. This project is called MFIP, and this is it have a repository if you want to check it out. That's it. Thank you. But now, if you have any questions, you know. Yes.
I'm interested in the use of view bounds.
Yes.
So, in which?
It's a bad thing.
Well, yeah, I was wondering why the targets of the view bounds were not just another set of type classes.
Yes.
Context bounds.
Because in my AST, I have concrete types. It's numerical expression. It's not that. It can be. maybe some improvement. I can use maybe some numerical expression data type class or something like that is parameterized in the type. At this moment, the AST it has no type parameters at all.
So which implicit conversions do you have defined? Is it just like integers to?
I have any numeric type,
Okay.
and I don't know, I have some helpers for two tuples, or from list to set literals. There are a lot of implicits around, but the implicits are open. You can add overloadings if you wanted. So, okay. So, okay.
Will this approach work with nested linear expressions where you build them up with brackets, nest them to arbitrary depth?
The question was, I don't know if I get it. The question is if this will work with nested linear expression.
Yeah.
What, for example?
Suppose there's like n variables and they're built up in a nested fashion.
Yes.
Where you take two, combine them, then take another expression.
Okay, you can have a list of.
No, not just a list, not just a flat list, but I mean nested one with brackets.
Yes. Okay, but you can, if your variables or something are specific, you have them in a list. You can do a fold over that list, and you can be creating, I don't know if that is what you mean, but you can accumulate that and you're creating a bigger model on every.
Yeah, I suppose, yeah.
Yes, you can use.
You had an expression that was still linear,
Yes.
but was,
Yes. Okay, I know what you mean.
One function of two variables fed into the next function of two variables, the third variable.
Yes, we can only use addition with linear expressions to keep the linearity. If you try to multiply two linear expressions, you will have a compile error because there is no type class instance for the multiplication operator. But yes, you don't have any problem with the nesting. I'm not sure. Maybe we can talk later. I'm not sure I understand your question. Okay.
Do you think instead of looking for the implicit conversions, you can model all the things that could be on the left-hand side, right-hand side as like a trait hierarchy?
Yes, I consider that. My major concern was like having the AST, like don't touching the AST, because I have the AST from a previous iteration. I wrote a Mathprog parser, Scala, and I wanted to keep it treat it as just data. But maybe I could have create a parallel hierarchy.
Then you cannot have the implicit ordering?
Yes. If you define your methods directly on your types, you can solve these problems by giving the right overloadings. But this won't be open to more overloadings. So I don't know, because, for example, you have some expressions in which you say that this value and this value and this value are in some set expression, and maybe you want to give some overloading so you can use a tuple and not a list or things like that. I don't know. I want it to be open. So the problem you have is that you have this ambiguity, and you have to use these view bounds because you want to keep the type. You need the view bounds because you need that the Scala see that he can use the implicit conversion on your type. It don't need to convert privilege to another type. So with the view bound, you are chaining implicit conversion some way.
Have you thought about using shapeless to track the arity?
Yes, I'm doing that. But I haven't lacked. Maybe one of you guys can help me with that. No, I'm trying. Yes, but yes, it's one of the things I want to work on. Yes, sure.
Have you thought about, so for your ops classes, you have three types.
Yes.
The first two, they determine the third
Yes.
one. And so you could make the third one a type member, which would be a little bit more explicit about that constraint.
Okay, that's nice. Nice consideration.
I don't know if it would have any practical difference, but it encodes that constraint a little bit more explicitly.
Yes, that it's not really an open type because it is determined by the other two types.
Right.
Okay, thank you. I didn't thought about it, but I think it's a great thing. Yes.
Seems very modern.
Yes. Okay, thank you.